So let us now understand the solubility of a gas in a liquid, the factors which affect the solubility of a gas in a given liquid. Two of the important factors which affect the solubility of any gas in a liquid solvent are pressure and temperature. So now we would explore the effect of pressure and temperature, right, on the solubility of a gas in a given liquid solvent, right? Starting with effect of pressure. So let me put effect of pressure. In general, if you have to talk about effect of pressure, I can put up a general statement that solubility of any gas increases with increase in pressure. So the general statement would be solubility of a gas would increase with increase in pressure, right? Now let us consider a system, right, in which a gas is allowed to dissolve in a liquid solvent at a fixed temperature in a closed container. So let us understand how this works. So first of all, let me put this all together, right? And now let us move on to the next part. So now look at this. We have a gas taken in a closed container, right? And it is taken with a liquid solvent. As you can see here, that there is gas in the upper part and there is solution in the lower part. Here the gas has attained equilibrium with this liquid solution. Now what do we understand by equilibrium? Remember, when you put gas in a closed container with a liquid solvent, initially the particles of these gas, they strike with the surface of this liquid, and some of them then lose their energy and would get dissolved in the liquid. This is called dissolution. At the same time, you also find that some of the gaseous molecules, they would attain more energy and would go back into the gaseous state. This is called evaporation. So dissolution and evaporation, they occur simultaneously. Initially, the dissolution is more and evaporation is less, right? But eventually, you find that the two rates balance out. So when the rate of dissolution and evaporation, that is the rate at which gaseous particles enter liquid solution, when this rate becomes equal to rate at which gaseous particles leave liquid solution. When these two rates become equal, we say a dynamic equilibrium is attained. Now here we can say that in the first figure we find that the gas has attained dynamic equilibrium, right? So in this case the system is already at equilibrium, which means the number of gaseous particles entering the liquid and the number of gaseous particles leaving the liquid, they would be equal. Now at this point, the concentration of gaseous particles in the solution would be remaining constant and it would not change, right? Let pressure of the gas here be equal to P and temperature be equal to T. Now, what happens is, in the second figure, we are disturbing the equilibrium. We are compressing this gas. By putting some more weight, we're compressing this gas. As the gas gets compressed, we find that the number of gaseous particles available per unit volume would increase, the pressure would also increase, and the equilibrium is disturbed. Now, according to Le Chatelier's principle, the system would try to restore that equilibrium. And how can system restore that equilibrium? By, getting the same pressure once again. How can the system attain the same pressure once again? By allowing more gaseous particles to move into the liquid solution. As more gaseous particles move into the liquid solution, we find that here the number of the pressure once again gets restored as before. It once again would become P, right? And you find that once the equilibrium is restored, more gaseous particles would be found in the solution, which means solubility of a gas would increase if you increase the pressure. This can also be understood with a different perspective. We may say that when you increase the pressure, the number of gaseous particles available per unit volume would increase. As a result, their collisions with the surface of liquid would also increase. And it is because of this that the rate of dissolution would increase, and hence you find more gaseous particles in the given liquid solution. Thus, we find that the gaseous particles would now dissolve more in the given liquid solution. So this is how we understand why with increase in pressure, the amount of gaseous particles in the solution increase, right? Now, a quantitative relationship between the pressure exerted by the gas over the surface of any liquid and its solubility in that liquid. A quantitative relationship between the two was established by a person called Henry. And this relationship was expressed by Henry in form of a law, which is then called Henry's law. So now let us move on to Henry's law. So, Henry's law now. So, as I've told you that Henry was the first person to give quantitative relationship between the pressure of a gas and its solubility in a given liquid solution. Now, the law states that the solubility of a gas in a given liquid at constant temperature is directly proportional to its pressure above the surface of liquid. So, very simple to understand that a solubility of a gas in a given liquid at constant temperature is directly proportional to its pressure above the surface of liquid. Now, inspired by Henry's work, a contemporary of Henry, John Dalton, he also started doing similar experiments in which, instead of taking a single gas which is in equilibrium with a liquid, he started taking mixture of gases. He started taking mixture of gases which were simultaneously in equilibrium with a given liquid solution at constant temperature. After doing a lot of experiments, John Dalton concluded. So let me give you the conclusion of John Dalton then, right? So this is Dalton's conclusion. Now this is going to be your Dalton's conclusion, which says that solubility, let me write down, solubility of a gas in a given liquid solution at constant temperature is a function of its partial pressure. Look at this, right? He used the term partial pressure. You have to understand this. Why? Because he was working with mixture of gases, right? And because he was working with mixture of gases, he used the term partial pressure, right? So, John Dalton, he did similar experiments, but with mixture of gases. Eventually, if solubility of a gas is expressed in terms of mole fraction, then the same conclusion given by Dalton can be expressed as. So now we consider solubility of a gas in terms of its mole fraction. So now let us put it in simple form, that mole fraction, this is the solubility, right? Mole fraction Xg of a gas in a given solution at constant temperature is proportional to its partial pressure above the surface of liquid solution. Look at this, everything done in a different way. We have, right. So now we have the Dalton's conclusion, and we also have the same conclusion expressed in terms of mole fraction of a gas. So here solubility is given in terms of mole fraction. Now today, after going through all these different conclusions, right, today the most modern form of Henry's law is given in different way. So let us understand the most commonly used or the most modern form of Henry's law. So I'm going to put this up like this. Commonly used form of Henry's law. So here, today, Henry's law is generally expressed like this. So let me show you how it is expressed. Okay? The law says that partial pressure for gas above the surface of any solution in a closed container at constant temperature is directly proportional to its mole fraction in solution. This is the most modernly used law, right? Henry's law in modern form, or the most common form of Henry's law, is like this. Okay, so let us put this all together, right? Now we can use the mathematical form of Henry's law. So all this, right, it can be expressed in mathematical form. So the mathematical form of Henry's law, mathematically, we have Henry's law given as, this is the pressure of gas, partial pressure of gas, and this is equal to Kh into mole fraction. So I can put this as, this is the partial pressure of gas, this is the mole fraction of gas in solution, and this is the Henry's law constant, or Henry's constant, we can directly put it like this is the Henry's constant, right? So this is the mathematical form of Henry's law, and you all should know this properly. It can be used for solving a lot of numericals also, right? And now I would show you a simple graph, and after that we would take up some characteristics of Kh. As you can see that if we plot a graph of, from the equation, P against X, partial pressure of gas against its mole fraction in solution, it should be a straight line, and slope of the line should be equal to Kh. This has been verified experimentally, and it has been found that indeed when partial pressure of HCl gas, right, when taken along with a solvent like cyclohexane, right, when a plot is given of partial pressure of HCl against mole fraction of HCl in cyclohexane, we find that we get a straight line. So P against X gives you a straight line, and if you take the slope of this line, you get the value of Kh for dissolution of HCl in cyclohexane at a given temperature, right? So this is about the basics of Henry's law. Now I'm going to give you some characteristics of Kh, right? And then we take up some practical applications of Henry's law. Okay, so let us take up the characteristics of Kh. The first thing, different gases have different values of KH for their dissolution in same solvent at same temperature, which means for different gases we have different values of KH. So every gas has its own value of KH for dissolution in the same solvent, right? So if you take different gases and consider their dissolution in the same solvent, their KH values would be different even if the temperature remains the same, right? The second important point, if KH for a gas is more, its solubility in a given solvent is less. It is simple to understand, right? We know that P is equal to KH into X. So for same pressure, if value is high, this value will be low. Very simple to understand that for the same pressure, if this value is high for a gas, then this value has to be low because product will be equal to P. So if this is more, this has to be less. So if KH of a gas is more, it indicates that its solubility will be less. So let me put this now together. Yeah. The next point. With increase in temperature, KH value for any gas increases. So if temperature increases, KH value also increases. So this is also one important thing to know, right? So three important characteristics of KH that if you take different gases, the KH values would be different for the same solvent, right? For the common solvent and for the same temperature, different gases have different values of KH. KH for any gas, if it is more, then its solubility would be less. And if you increase the temperature, the KH value for any gas would always increase, which in other words would mean solubility of a gas would decrease with increasing temperature. Clear? So these are the characteristics of KH. So let us go to the applications of Henry's law. Now, three important applications of Henry's law. One, to increase the solubility of CO2 in soft drinks and soda water, the bottle is sealed under high pressure. You know what? When these soft drinks and soda water, which have carbon dioxide as a gas in them, in order to enhance or increase the solubility of CO2, generally these bottles are sealed by keeping very high pressure of CO2. Keeping very high pressure of CO2 as per Henry's law would ensure that the amount of CO2 dissolved in soft drinks or soda water would be very high, and which is needed. The second important application of Henry's law is to avoid a condition called bends. Generally, scuba divers, deep sea divers, when they dive in and as they move towards the bottom of the sea, there is very high pressure on them. And the air tank that they take in, right, they would be inhaling air under very high pressure. As a result, there would be more amount of gases dissolved in their blood. Now, if they take normal air, then oxygen and nitrogen would start getting into their blood. Oxygen would be utilized for metabolic activities, but nitrogen would remain in blood. Now, suddenly, when a scuba diver moves up, at the surface of the sea, the pressure would be less, and so the dissolved oxygen would immediately get evolved from the blood in form of nitrogen bubbles, and these bubbles would generally be formed in the capillaries, and many a times they would block the flow of blood. This results into divers feeling giddiness, headaches, and at times they can even get unconscious. This condition is ideally called bends. So, this is ideally called diver's bends basically. So, diver's bends or simple bends, right? And to avoid bends, what they do is the air that is taken by these scuba divers is diluted with helium. You know what? By putting helium, what do you think should happen? Helium has a very high value of Kh. Helium has a very high value of Kh. What does that mean? It means that the solubility of helium is very, very less. Because the solubility of helium is very, very less, diluting the air with helium would ensure that the amount of gases getting dissolved in blood would be reduced. Now, you can see the special composition, 11.7, 56.2, and 32.1. If you properly look at these percentages, it is, as such, the molar mass of helium is slightly less than 4. So this is basically, if you properly look at this, this is basically 4 3s are 12. So this is like, 3 moles of helium. So if you want to take the mole ratio, I can put the mole ratio. Mole ratio here would be, helium would be 3 moles. Nitrogen, the molar mass is 28. So this is going to be 2 and this is going to be 1. So if you ever forget this, just remember that helium, nitrogen and oxygen, they are in the ratio of 3:2:1, mole ratio of 3:2:1, right? And the last thing that you have to know is like mountaineers and the people living at higher altitudes. At higher altitudes, the air is thin, the pressure is low, and so the partial pressure of oxygen at higher altitudes would be very, very less. As a result, the amount of oxygen getting into the lungs and then getting dissolved into the blood would be very, very less at higher altitude. And as a result, because the amount of oxygen reaching the cells would be less, people would start feeling weak, and many a times their thinking capacities are also impaired to a small extent. And this condition is called anoxia. So people living at higher altitudes would suffer from anoxia. To avoid this, generally, mountaineers and people living at higher altitudes, they are supplemented with oxygen cylinders, and higher pressure of oxygen would ensure that there is enough oxygen in the blood. So these are 3 important applications of Henry's law. Let us now understand the other factor which affects the solubility of gases in liquid solvent. First one was effect of pressure. The second parameter that we have to check is effect of temperature. Now here you have to know one important thing, that process of dissolution of any gas in liquid solvent is an exothermic process. This is very important, that dissolution of a gas in any liquid solvent is an exothermic process. You have to know that, right? So yeah, it is an exothermic process. So now I hope you understand this, that thus increase in temperature decreases the solubility of any gas in a given solvent. Why? Because this is as per Le Chatelier's principle. As per Le Chatelier's principle, right? So you have to know this, that Le Chatelier's principle, as per Le Chatelier's principle, if forward process is exothermic, that is the dissolution of gas in a given liquid, that's the forward process, and backward process is evolution of the gas from that liquid. Now, if forward process is exothermic, the backward process would be endothermic, which is evolution of the gas from the liquid solvent. Now you know that if dissolution is an exothermic process, increasing the temperature, the system would try to favor, in order to lower the temperature, system would try to favor endothermic step, and for favoring endothermic step, it would start favoring the backward process of evolution of a gas. And so here we say that with increase in temperature, solubility of any gas in a given liquid solvent would decrease, right? So that is the second parameter, the second factor that we had to know, right? So this completes the the gas in liquid type of solutions. We may have one or two numericals after this. Now let us solve a numerical which is based on Henry's law. This is one of the numericals given in the textbook, and I'm going to do that. Now here, as they have given, H2S is a toxic gas used for qualitative analysis, and solubility of H2S in water at STP is given. Thus, normal Henry's law, the mathematical form has solubility given in terms of mole fraction. Here, it is given in terms of molality. We would be, converting this into mole fraction, and you have to calculate KH. So what should be done now? So a simple way of doing it is, we first of all interpret 0.195 molal solution. It means it is 0.195 moles of H2S in 1 kg water. Now I can even elaborate and say 1 kg water is nothing but 1000 divided by 18, which is about 55.55 moles. All right. Now, what I can do is I can, use the formula P is equal to KH into X. That's mole fraction. Now, pressure. Now, you know that this is STP. At STP, the pressure is 1 bar. And X here is moles of H2S upon moles of H2S plus moles of water. Now we can put the values here. Moles of H2S would be 0.195. This is 0.195. And this is 55.55. So now I can make this We can put it across here. And now let us put the values. P is 1 bar is equal to KH into 0.195 divided by 0.195 plus 55.55 would be about 55.745. Therefore now KH should be equal to 55.745 into 1 upon 0.195 bars. And this would give us, let me put this in calci and let me find out. This is 55.745 divided by 0.195, which gives you 285.8. Remember, KH will have the same units as pressure, right? Remember this. KH will have the same units as the pressure. If you take this in ATM, this will be ATM because mole fraction is without any units. So now what we can have is, all right. All right. So I hope you've understood this, this kind of numerical. These are all based on Henry's law, right? And they are pretty simple, right? All right, let us take up one more numerical from textbook. This is one of the numericals which has been frequently asked as doubt, and so I'm doing it here. Look at this. Air is a mixture of O2 and N2 in volume ratio 20 and 79 respectively. Now water is in equilibrium with air at a pressure of 10 atm. So there is water in a container and there is air in that container which has a pressure of 10 atm. And now they say that you have to find out the composition of gases in water. So you have to find out what would be the mole fraction of nitrogen and mole fraction of oxygen in water. Now KH for oxygen and nitrogen are given. They are given in mm. So we need to evaluate pressure in mm, right? So first of all, because there is air taken in a closed container with water at a pressure of 10 atm, here the total pressure is 10 atm, which would be the pressure of nitrogen and oxygen together. So let us find out what would be the partial pressure of nitrogen and what would be the partial pressure of oxygen, so that we can find out their respective mole fraction, right? For example, we would be using this formula that pressure of nitrogen, partial pressure of nitrogen should be equal to KH for nitrogen into mole fraction of nitrogen. And the other equation that we need to use is for oxygen, which is like KH for oxygen into mole fraction of oxygen, right? Now the point is, these values are already given. These values are already given, right? The KH for nitrogen given is 6.51 into 10 raised to 7 mm. This value given here is 3.3 into 10 raised to 7 mm. And the question asked is, you have to find out mole fraction of nitrogen and mole fraction of oxygen. For that, you will have to know these values. You have to know the partial vapor pressure of nitrogen and oxygen in that container. Now, how do we do that? You know that you can very easily calculate partial pressures by multiplying mole fraction with total pressure. However, here we have the volume fractions given, right? We don't have the mole fraction. So because they are together under same conditions of temperature and pressure, the volume ratio can be taken as the mole ratio also. So we can take this up as pressure of nitrogen, partial pressure of nitrogen is equal to total pressure 10 multiplied by, for nitrogen it is 79 divided by 100. I think it is 99, but we approximated to 100 because otherwise the calculations would become a little more complex. So let us put it like this, right? And this, if you multiply this with this would be in ATM. So if you multiply this with 760, you will get your answer in mm, right? So into 760 would give us the answer in mm. This comes to somewhere close to 6004 mm if you multiply. And partial pressure of O2 would be 10 into 20 by 100 into 760, which would give us 1520 mm. So now we have this, we have this mm thing. So all we need to do is we have this. Sorry, we need to put this up together. And just a moment. Let me put this up all together so that I have more space here. All right. Now what? I just have to calculate the mole fraction. So mole fraction of nitrogen then would be equal to, for nitrogen it will be 6004 divided by 6.51 into 10 raised to 7. I think that's the that's the value for KH for nitrogen, and this gives us about 9.2 into 10 raised to minus 5 as the value. And mole fraction of oxygen would be 1520 divided by the 3.3 into 10 raised to 7 as they have given, which gives us 4.6 into 10 raised to minus 5. Thus, it was not very difficult. We have a few calculations which you can attempt using log table if they don't provide, but otherwise things are not very difficult here. So I hope you've understood this numerical. It is not at all difficult. And such numericals can be asked, so pay attention to them, right? More numericals in my regular lectures we've already done, right? All right then. I hope you've understood Henry's law properly. In the next video, I would be putting up Raoult's law.